Now we just saw how to model a cell EMF. Now, now let's try to graph the potential difference across this resistor. Okay, the potential difference and current through this resistor as I change R. You understand? So I'm trying to find out an I versus R graph for the current this, or I1 you can say. Okay, so I1, the current through this resistor versus R. Okay, how do I do that? As I change this R, I want the current change that will happen. Okay, so let's write the equation. We had seen that this this I1 is nothing but E upon R plus R, right? So I is equal to, I now name it I is equal to E upon R plus R. So how does it change? How does it change? Yes? Yeah? Fine. What will be the nature of the graph? Yes? Will it be a straight line? Will it be a straight line? Will it be? Look, this I am plotting on the y-axis, and and this I am plotting on the capital R, which seems to be currently a constant. It is not no longer a constant. It is variable, right? Correct. Now whenever you are dealing with the variables, so if it is easy, we have been dealing with graphs and the equations for the graphs, we have been dealing with the straight lines, the circles, the ellipses, right? So let us try to convert this in terms of y and x. So I write I as y, E is a constant, R which is a variable, right? This varies, so I write it as x, and this is a constant, right? So what does that look like? It is y into x plus R is equal to E. Okay. First of all, will it be a straight line? Will it be a straight line? Yes. The equation for a straight line is always a linear equation in two variables. Okay. Only when it is a linear equation in two variables will it be a straight line. And what do we mean by that? It should be of the format ax plus by plus c is equal to 0. Then only will it be a straight line, right? Now if you look at this, this is the x and y first of all multiplied together. In a straight line, x and y both had powers 1, but they were separated, right? There was no multiplication term with that. So this is xy plus ry is equal to e. Okay, fine. Now what happens? what happens is, first of all, I have got a product of x and y, and there is a y separate. So whatever it is, we do not know it yet, but it is not a straight line. So the graph is not a straight line. This is not a straight line. That much I am pretty sure. Yes, yes, yes. Now let us try to get a hang of what is happening. When this x is 0, what is my y? My y is the maximum current. So it's E upon R, right? So this place is E upon R. When small r is equal to 0, then this when x, I'm sorry, when x is equal to 0, it is E upon R. Okay. Now what happens? What does it tell you? That if you accidentally short this, okay, if it is a dead short, it's called a dead short. Okay, dead short is connecting this by not a superconductor, but a very pure conductor, say a copper wire, okay, or a copper strip. Now the moment you do that, it will start drawing a current that is E upon R. Okay. Now even if this cell is about 12 volts, and say the internal resistance is 0.1, it will start drawing a current of 120 amperes. Okay. Or say the copper strip by which you have shorted it, it is itself of a resistance 0.1. So it becomes 12 upon 0.1 plus 0.1. That makes it
12 upon 3.2.
60 amperes, right? Now 60 amperes. Now what is the joule heating in this? It is 60 square I square R. So that is 3600 into 0.1. That is nothing but 360 watts. 360 watts. Okay, that's a lot of heat. So you'll find that the strip has become hot. Okay, and if it was say not that thick the strip, or its surface area is less, or maybe it's a wire, then you'll find that it will melt. It will not be able to handle that much power. Okay, and it's good that it melts, otherwise it will burn the whole battery. Okay, because this battery is not meant to carry currents of the order of 60 amperes. Okay, they do not carry, they're not designed to carry that much amount of current. Okay.
The copper wire is melted, but then also the current keeps coming along.
No, if it melts, it breaks. If it melts like a fuse, it breaks. Like a fuse, it breaks. And that's the end to it. So it's good that it breaks, and that's why you use fuses. But if I say that I keep this dead short there, then there is a power of 360 watt that will be generated here. Okay, in a sense you can say it is good here, as in the case of friction we say it's a necessity evil. It's good that there is a 0.1 here, because if this 0.1 would not have been there, the current that it would have drawn would have been only the resistance, or the only resistance that the circuit would have faced would have been this 0.1, and the current would have been 120 amperes, and the power would have been 120 square into 0.1. 120 square is equal to this into 0.1 is this. It would have been 1.4 kilowatts. Straight away 4 times. Okay, 1440 upon 360 is 4 times. So the power dissipated would have become 4 times. Fine. This is not to say that we use this internal resistance as a protection for the circuit. No, not at all. There are better ways to protect. There are better ways to protect the overcurrent through this. One of them is overcurrent relay that you can use. So the moment it senses a current, say more than 30 amperes or 40 amperes, it'll cut the supply. Correct? But I'm just telling you what you should expect. Had this R not been there, and if you would have shorted it with the zero resistance, it would have started carrying an infinite amount of current. Okay, and the whole battery would explode due to the heat generated, the gases that would have been generated, the fumes, and the whole battery will go away. It will fall apart, right? A total chaos. So this is why it is due to this that you find it limited on the y-axis at E upon R. Had this not been there, it would have gone to infinity. It would have gone to infinity, right? Correct? So fine. The first thing is here. Now, what about the second one? Okay. So as I start increasing this x, okay, I do not know how it will behave, but at x tending to infinity, the whole thing will tend to 0. Okay. Now I know that it cannot go like that. It is not a straight line. This we have overruled. It's not this. But still I'm drawing it, right, to give you an idea of what will happen. If it is going to now if this is not a straight line, it has to be a curve. Correct? If it's a curve, it can either be this kind of curve, not necessarily cutting it here, okay, maybe this kind of curve, or this kind of a curve. Okay, if it is this kind of a curve, it tells me that for a finite amount of capital R, the current will go to 0, which will never be the case. Okay, howsoever high you make your capital R, this current will not go to 0. It cannot. Correct? So we had already overruled this. We also know that this will not be the graph. Okay, so then what? Yeah, because it cuts it here. It tells you that at some finite R, at R, the current goes to 0. Okay, the moment you cut the x-axis, the current goes to 0. Right?
That's not possible.
Not possible. Okay, then what? Then this is asymptotic. You know what do we mean by asymptotic? That this kind of starts tending to 0 as I make the R very high, or as R tends to infinity. So what I'm trying to say is that this graph goes like that, and it can keep on becoming nearer and nearer to the x-axis as my R goes farther and higher till at infinity it goes and touches it. Okay, and since these two touch at infinity, and I do not have infinite length of paper with me, so what do we do? What is the way to show that? What is the way to show that? We make this curve parallel to the x-axis. Okay, we have been told that the parallel lines never meet, but the actual definition is that the parallel lines meet at infinity. So whenever two things tend to meet at infinity, we say that they become parallel. So the way to show this on the graph is this. So let me draw a fresh one, and with whatever we have discussed, we are saying that that the graph starts at some finite e upon r, and from here it goes down, 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 and it'll it'll go somewhere here and it'll become parallel. I leave it at that. Okay, I cannot keep on stretching it because it never ever cuts the x-axis in the finite region that is available to you.
So how do you figure that never gets it?
Because we have the equation is y is equal to e upon x plus r, and we know that y tends to 0 if x tends to infinity. It cuts it, but at infinity. Only when the value of capital R goes to infinity does it cut it there. Okay, so it cuts it at infinity. That's why I've shown this line to be parallel and just left it at that. Okay, do we get that? Now how about the potential across? How can I plot the potential difference across the resistor?
So maybe that point E is smaller.
This point will be E by, this point will be E upon small r. Yes. What have we shown here? Yeah, right. This is E upon small r. This is the point where x is equal to 0, right? So the moment you put x as 0, it becomes E by small r, right? Now, how about the potential across the resistor? That we had called VAB, and that was what? That was I into this I, right? My I is equal to E upon R plus R. That is I into capital R. Now what is that equal to? This is equal to E upon R plus R into capital R. Now how about this? Yes? So how do we go about it? Let us again convert whatever I am trying to plot on the y-axis in terms of y. Okay? But write it in terms of y and write this in terms of x. So it is Ex upon x plus r. Okay? All are constants, x and y's are variables. Okay? Now what? So it becomes xy, I multiply this there, xy plus yr is equal to ex. It again cannot be split in terms of x and y separately, so it cannot be a straight line. That is the first point you should keep in mind, right? So it is not a straight line. Now let us put some endpoints. What happens? What happens to the graph? Let's say if r is equal to 0, what happens? Yes? This will become 0, correct? So this is one of the points, correct? Okay. Now what happens when r tends to infinity? See, r tending to infinity means this is an open circuit. Infinity. Understand? This is an open circuit. It is as if you have connected no resistor. Or if you have connected a resistor, it is so great, the value is so high that the current goes to 0. This we had seen there, that the current tends to go to 0 if your R becomes infinity or tends to infinity. We never say that it becomes infinity. Infinity is kind of infinity. It's a number that is larger than the largest that you can even imagine. So you never say that something becomes infinity. You only say that it tends to infinity. Because the moment something becomes infinity, infinity does not remain infinity, it becomes finite. Why? Because you cannot become infinity, you cannot touch infinity. Okay? If it is touchable, it means it is limited, and if it is limited, it's finite. If it's finite, it's not infinite. Okay? You get the hang of it? Okay? So it tends to infinity. So if it tends to infinity, the current goes to 0. If the current goes to 0, then the potential across this also is what? Let's try to see. Let's try to see the potential across that. It seems that the potential is 0. Seems that the potential is 0, but we'll see what it is. See, if so we are trying to find out limit R tending to infinity VAB. Okay, that becomes limit R tending to infinity ER upon R plus R. Okay, so that is why you were taught limits in class 11th. Okay, now if I put infinity here and infinity here, it is of the form infinity upon infinity, which is an indeterminate form. Now what do I do? What do I do to resolve it? It becomes, I divide the numerator by R, so it becomes ER upon R divided by R plus R upon R. Get the point? Now what happens? What does the numerator become? The numerator becomes R upon R is E, right? And the denominator becomes 1 plus R upon capital R. Correct? See that? Now, this R is tending to infinity. So, something upon infinity tends to 0. So, this becomes 0. So, the denominator remains 1 plus 0, that is 1. So, my potential becomes E. Now, again the same thing. I know it is not a straight line. Okay? Then it has to be a curve. So, it could be a curve like that, or it could be a curve like that. Okay, this seems to be increasing with the increase in R and will tend to infinity as R tends to infinity. This has the tendency to turn like that and maybe approach I'm sorry, and maybe approach VAB equal to E, you see, as R tends to infinity. So out of these three curves, this magenta goes away, this yellow goes away, we are left with this greenish blue, right? So this will be the VAB versus R curve. Okay, you get the point? Fine.